Explanation 1. Formal definition of the traveling salesperson problem (TSP) and mathematical formulation. The traveling salesperson problem asks if a salesman has to visit a list of cities exactly once and come back home. What is the shortest possible round trip? Mathematical view. Let the set of cities be V equals the set of numbers from 1 to n. For every ordered pair ij, we have a non-negative distance c, ij the cost to travel from city I to city j. A tour is a permutation pi equals pi sub 1 pi sub 2 through pi sub n of the cities with pi sub n plus 1 equals pi sub 1 to return home. The length of the tour is cost pi equals sum from k equals 1 to n of c pi sub k plus 1. Goal. Minimum over pi, where pi is a permutation of v of sum from k equals 1 to n of c pi sub k plus 1. Think of the cities as houses on a playground, and the salesman as a child who wants to run to each house once and end, where he started using the smallest amount of chalk dust distance. The problem is NP hard, meaning we do not know a fast way to solve it for huge N. Branch and bound is an exact method that systematically explores possibilities while cutting away branches that cannot improve the best tour found so far. Number 2. Construction of the search tree, state representation and branching decisions. A branch and bound algorithm builds a search tree where each node represents a partial tour. Some cities have already been fixed in a specific order. The rest are still open. State representation. Visited set S. The cities already placed in the tour, for example, open brace 1, 4, 3, close brace. Current city V, the last city added to the partial tour. Remaining edges, all possible next moves from V to a city not in S. Partial cost P, sum of the distances already traveled. Branching rule. From a node, open parenthesis S, V, P, close parenthesis, we create a child for each city U not in S. The child state becomes S prime equals S union open brace U close brace. V prime equals U. P prime equals pi plus C subscript VU. This is like a choose-your-own-adventure book. At each page node, you have several storylines, branches to turn to, each adding a new city to the trip. The root node starts with a single city, often city 1, as the starting point. S equals open brace 1 close brace, V equals 1, P equals 0. The tree height is n because after n decisions, we have visited all cities and must close the tour by returning to the start. 3.1 Reduced cost matrix, held carp bound. Start with the original distance matrix C equals C sub ij. For every row I, subtract the smallest element in that row. Call it R sub I. This makes each row have a 0. For every column J, subtract the smallest element in that column after the row reduction. Call it S sub j. The reduction cost is sum of R sub I over I plus sum of S sub j over j. Add this to the partial cost P. The result is a lower bound for any tour that respects the already fixed edges. When we branch, fix an edge I to j, we set C sub ij equal to infinity for the opposite direction to avoid subtours, and recompute the reduction. Imagine you have a set of children, each must receive a chocolate bar. You first give each child the smallest bar they could possibly accept, row reduction, and then make sure each type of chocolate is given out at least once, column reduction. The total of those smallest bars is a guaranteed minimum amount you will spend, no matter how you later arrange the bigger bars. 3.21 Tree relaxation. Remove city 1, compute a minimum spanning tree on V without 1 using the current distance matrix. Find the 2 smallest edges incident to city 1, say 1 to A and 1 to B. The weight of the minimum spanning tree plus those 2 edges is a lower bound. If the one tree happens to be a Hamiltonian cycle, each node degree 2, it is already a feasible tour, giving both lower and upper bound. The one tree bound is often tighter than the simple reduced cost bound, especially when the graph is nearly Euclidean. Both bounds are cheap to compute, polynomial time, compared with solving the whole traveling salesman problem, yet they prune many branches. Upper bound generation via heuristic tour, for example nearest neighbor or greedy insertion. While the algorithm is searching, it constantly needs a current best complete tour, upper bound, to compare against lower bounds. Good heuristics give a short tour quickly, shrinking the search space. 4.1 Nearest neighbor and ends. Start at a chosen city, often city 1. Repeatedly go to the closest city that has not been visited yet. After all cities are visited, return to the start. Kid analogy: imagine you are eating candies placed on a table. You always pick the candy that is closest to your hand. In the end, you have taken all candies, maybe not in the perfect order, but you finish quickly. 4.2 Greedy insertion, also called cheapest insertion. Begin with a small subtour, usually the edge between the start city and its nearest neighbor. While there are still unvisited cities, find the city K and the edge I and J in the current tour that increase the total length the least when K is inserted between I and J. Insert K there and repeats. Analogy: building a train loop. You already have a short loop and you keep adding stations at the cheapest place to extend the loop. Both heuristics run in O of n squared time and produce tour that are often within 10 to 30% of optimal for Euclidean instances. The best tour found by any heuristic becomes the initial upper bound for the branch and bound process. If later the algorithm discovers a better complete tour through exhaustive search, the upper bound is updated, allowing more aggressive pruning. Bounding conditions. For a node with partial cost P and lower bound L, if L greater than or equal to U where U is the current best upper bound, then the node is fathomed discarded. The intuition is simple. Even the best you could hope for from this node is not better than what you already have. Dominance/symmetry rules. Edge dominance. If two edges ij and ik have the same cost, and the algorithm has already explored the branch fixing ij, we can skip the symmetric branch fixing ik to avoid duplicate work. Fixed city ordering. Force the tour to always start at city 1 and to visit cities in increasing numeric order when the partial tour is empty. This removes equivalent tour that are rotations of each other. Elimination. When a partial solution creates a small closed loop that does not include all cities, we can prune because any extension would require breaking the loop, which violates the definition of a tour. Depth limit optional. Sometimes a user caps the depth of the tree stop branching after fixing 3 edges and solves the remaining with another exact method such as integer linear programming. This hybrid pruning reduces memory usage. Together, these rules keep the tree from exploding and focus the search on promising regions. 6. Priority queue management and node selection strategies. Best first, depth first. The algorithm must decide which node to explore next. It keeps all live nodes in a priority queue PQ. 6.1 Best first, a star-like. The PQ orders nodes by their lower bound L, smaller first. The node that looks most promising, smallest possible total length, is expanded. This often finds the optimal solution quickly, but may require a lot of memory because many nodes stay in the PQ. 6.2 Depth first, DFS with backtracking. Nodes are stored in a stack. The most recently generated node is expanded. Memory usage is low, only the current path plus a small fringe. The algorithm may wander deep into a bad branch before finding a good solution. However, when a good upper bound appears, a lot of later nodes are pruned. 6.3 Hybrid, best first plus depth first. A common practical choice is depth first with best first bound updates. 1. Use DFS to quickly reach a complete tour, gives a decent upper bound. 2. Switch to best first for remaining nodes to aggressively prune. 6.4 Implementation tip. In most languages, a binary heap priority queue supports O of log m insertion and extraction where m is the number of live nodes. For DFS, a simple array or linked list works. The selection strategy dictates the trade-off between speed and memory, and the best choice often depends on the size of the TSP instance and the hardware available. 7.1 Initial upper bound nearest neighbor. Start at city 1. The nearest unvisited city is 2 with cost 10. From 2 go to the nearest not visited city 4 with cost 25, cumulative 35. From 4 go to the nearest not visited city 5 with cost 15, cumulative 50. From 5 the last city is 3 with cost 20, cumulative 70. Return to 1 with cost 15, total 85. So upper bound U equals 85. 7.2 Root node only city 1 fixed. Partial tour 1 to ... Partial cost P equals 0. Compute reduced cost matrix. Row minima are 0, 10, 15, 15, 15. Subtract from each row. Column minima after row reduction are all 0. Reduction cost equals 0 plus 10 plus 15 plus 15 plus 15 equals 55. Lower bound L equals P plus 55 equals 55. Since L is less than U, keep the node. Push it into the priority queue with priority 55. 7.3 Expand node with smallest L still root. Branch on the second city, choose each possible next city. First, add edge 1 to 2, new partial cost P equals 10, set the cost from 1 to 2 to infinity to avoid returning immediately. Reduce the matrix, new reduction cost equals 45 after calculations. Lower bound L equals 10 plus 45 equals 55. Second, add edge 1 to 3. Partial cost P equals 15, lower bound L equals 58. Third, add edge 1 to 4. Partial cost P equals 20, lower bound L equals 60. Fourth, add edge 1 to 5. Partial cost P equals 25, lower bound L equals 62. All have lower bound less than 85. Insert them into the priority queue. 7.4 Next node 1 to 2 because it has the smallest lower bound 55. Current partial tour 1-2. Branch on the third city from city 2, possible next cities are 3, 4, 5. Edge 2 to 3, partial cost P equals 10 plus 35 equals 45. Reduce the matrix, reduction cost equals 30, lower bound L equals 75. Edge 2 to 4, partial cost P equals 10 plus 25 equals 35. Reduce the matrix, reduction cost equals 30, lower bound L equals 65. Edge 2 to 5, partial cost P equals 10 plus 30 equals 40. Reduce the matrix, reduction cost equals 32, lower bound L equals 72. Insert these three nodes. The smallest lower bound in the priority queue is now the node 1 to 2 to 4 with lower bound 65. 7.5 Expand 1 to 2 to 4. Partial tour 1-2-4, partial cost P equals 35. Remaining cities are 3 and 5. Branch. Edge 4 to 3, partial cost P equals 35 plus 30 equals 65. Reduce, reduction cost equals 12, lower bound L equals 77. Edge 4 to 5, partial cost P equals 35 plus 15 equals 50. Reduce, reduction cost equals 10, lower bound L equals 60. Node 1-2-4-5 gets lower bound 60 and is inserted. Now the priority queue minima are 55 for node 1 to 3, 58 for 1 to 4, 60 for 1-2-4-5, and so on. 7.6 Expand node 1 to 3 with lower bound 58. Partial tour 1-3, partial cost P equals 15. Branch options are 2, 4, 5. Edge 3 to 2, partial cost P equals 15 plus 35 equals 50. Reduction gives lower bound approximately 78. Edge 3 to 4, partial cost P equals 15 plus 30 equals 45. Reduction gives lower bound approximately 70. Edge 3 to 5, partial cost P equals 15 plus 20 equals 35. Reduction gives lower bound approximately 64. All lower bounds are greater than 55, none improve the current best. 7.7 Expand node 1-2-4-5 with lower bound 60. Tour so far is 1-2-4-5, partial cost P equals 50. The only city left is 3, so we add edge 5 to 3 with cost 20 making P equals 70. Close the tour by returning 3 to 1 with cost 15, total 85. We have found a complete tour of length 85, the same as our initial heuristic, so upper bound U remains 85. 7.8 Continue expanding remaining nodes. The node 1-2-4-3 has lower bound 77 greater than upper bound, so it is pruned. All other nodes in the priority queue have lower bound at least 62, also greater than or equal to upper bound, so they are pruned. The search finishes with the optimal tour 1-2-4-5-3-1 of length 85. Takeaway: even on a 5-city problem, the lower bound calculations cut away many branches, and the algorithm proves that the nearest neighbor tour was already optimal. 7.9 Summary of steps. Table columns. Step node partial tour PL action. Row 0 node 1 P0 lower bound 55 action keep. Row 1 node 1 to 2 P10 lower bound 55 action branch. Row 2 node 1 to 2 to 4 P35 lower bound 65 action branch. Row 3 node 1 to 2 to 4 to 5 P50 lower bound 60 action complete tour equals 85. Remaining rows, other nodes have lower bound greater than or equal to 85, action prune. Section 8, Time complexity and space complexity analysis of the branch and bound algorithm for traveling salesman problem. Subsection 8.1 Worst case time complexity. In the worst case, the algorithm may have to enumerate all possible permutations of the cities. That is, open parenthesis n minus 1 close parenthesis factorial divided by 2 tour for a symmetric traveling salesman problem. For each node, we compute a lower bound, which typically costs O of n squared, matrix reduction or minimum spanning tree. Hence, the theoretical worst case time is O of open parenthesis n minus 1 close parenthesis factorial semicolon n squared close parenthesis. This is exponential and explains why branch and bound is not polynomial time. Subsection 8.2 Practical average complexity. In practice, the bound functions are strong, and a large fraction of nodes are pruned early. Empirical studies show the number of examined nodes grows roughly like c to the n, with c approximately 1.5 to 2 for Euclidean instances, far smaller than open parenthesis n minus 1 close parenthesis factorial. Subsection 8.3 Space complexity. The algorithm stores the live node list, priority queue, and the data needed for each node, partial tour, partial cost, bound matrix. If at most b nodes are kept simultaneously, space is O of b times n. Depth first uses only O of n stack space, very low. Best first may keep thousands of nodes, leading to tens of megabytes for n approximately 50. Thus, space is pseudo-polynomial. It depends on the branching factor and pruning efficiency rather than on a fixed function of n. Subsection 8.4 Summary table. Column headings: metric, worst case, typical, practical case. Time: O of open parenthesis n minus 1 close parenthesis factorial semicolon n squared close parenthesis exponential. Typical practical case: approximately O of c to the n with 1.5 less than or equal to c less than or equal to 2. Space: O of b times n. B can be exponential. Typical practical case: O of n for depth first search, O of 10 to the 4 nodes for moderate n. The exponential nature is unavoidable for exact traveling salesman problem, but strong bounds and good heuristics keep the algorithm usable for instances up to a few hundred cities on modern computers. 9 Practical implementation considerations: data structures, parallelization, and integration with other exact methods. 9.1 Data structures. Distance matrix: store as a two-dimensional array double cost, open bracket n close bracket, open bracket n close bracket period. For sparse graphs, use adjacency lists. Node record: struct containing. Struct node open brace bits at visited semicolon, which cities are fixed fast check, int last city semicolon current end of partial tour double partial semicolon p, double lower bound semicolon l double reduced matrix, open bracket n close bracket, open bracket n close bracket semicolon copy for bound calculations, or store only row / column minima close brace. Using a bit set, for example uint 64t, for n less than or equal to 64 makes set operations O1. Priority queue: binary heap std double : priority queue in C++ or heap in Python keyed by lower bound. Stack for DFS: simple vector push / pop. 9.2 Parallelization. Branch and bound naturally splits into independent subtrees. Master worker model: master holds the global best upper bound U and distributes unexpanded nodes to workers. Dynamic load balancing: workers request new nodes when they finish a subtree. The master may prune nodes that become obsolete because a better U was found. Shared bound updates: use atomic operations or lock-free structures, so that when any worker discovers a better tour, all others can immediately prune. Parallel B and B can give near linear speedup for medium-size instances, up to 30 to 40 cores before communication overhead dominates. 9.3 Hybrid exact methods. Cutting plane plus B and B: use a linear programming relaxation, for example Miller-Tucker-Zemlin formulation, to obtain a stronger lower bound, then feed the bound into B and B. Branch and cut: combine B and B with generation of violated subtour elimination, constraints on the fly. Iterative deepening: first run B and B with a depth limit, solve the remaining subproblem with an ILP solver, then increase the limit. Memoization: cache lower bound results for identical subproblems, same visited set to avoid recomputation. 9.4 Implementation tips for a kid-friendly project. Start with a tiny graph 4 to 5 cities, and print every step. This makes the algorithm visible. Use colors to show visited cities, the current partial tour, and pruned branches. Provide a button show lower bound that runs the matrix reduction and displays the numbers. Let the user pick a heuristic nearest neighbor or greedy insertion, and watch how the upper bound improves. If you add parallelism, you can run 2 branches side by side in 2 windows and see which one finishes first. Following these practical suggestions will make the branch and bound TSP solver both efficient and easy to understand even for beginners.